Okay, this video is to go over ionic compounds. So the first thing is the definition. Ionic compounds form when electrons are being transferred. You want to make sure you always use that word transferred. New York State likes to use that word, and it simply means an electron is going from one atom to another. So electrons are transferred from a metal to a nonmetal. Whoops, non-metal. So there's our basic definition. So then we can get right into the metals versus the nonmetals. Metals lose electrons. When they lose electrons, they become positive. Their charge after losing electrons is called their oxidation state. And you can find it on the periodic table right up here in the top right corner. So, you know I always refer to them as left side losers. So your metals are your left side losers because they tend to lose electrons, and if they lose a negative, they become positive. All right, the nonmetals gain electrons. And when they gain electrons, they're gaining a negative charge, so they become negative. And their charge after gaining those charges, again, is called their oxidation state. And again, you're going to find it in the top right corner of the element on your periodic table. Write the oxidation number for each and indicate how many electrons it's gaining or losing. So let's start off with O, oxygen. That's a nonmetal. It gains 2 electrons. Now, how did I know that? There's multiple ways I know that. First of all, oxygen's valence is 6, and it's a nonmetal very close on the right side here of the table. So to go from 6 to 8, it would have to gain 2. So that's how I got this. Its oxidation state, if it gained 2 negatives, it would be a -2, and that is what it is in the top right corner. Let's take a left side loser. Let's take sodium. Sodium is a metal. It would like to lose 1 because it has 1 valence and it's in group 1. And its oxidation state would therefore be a +1. I want you to go through the rest of this chart, filling in any group 1, group 2 metals, and any nonmetals, but do not choose a noble gas. All right, so I don't want you to choose transition metals for this activity. Just choose group 1 or group 2 metals, or choose a nonmetal. Next, if we want to actually bond them, if we want to transfer electrons from one to the other, we have to crisscross. So, calcium and fluorine. Now we go back to that ionic bond dance, the cha-cha slide. So you go charge on the left, charge on the right, crisscross, and that'll always give you the right formula for an ionic compound. So, calcium, I look it up, it's a +2. Fluorine, I look it up and it's a -1. I crisscross those numbers and I get CaF2. That would be its chemical formula, and it's always the same. It never changes because calcium has 2 to lose and fluorine just gains 1. So I like to think of it with these little markers. If I'm calcium and I have these 2 valence electrons, I can lose 2. I want to lose 2. My next inner shell will be full if I lose 2, so that would be perfect for me. Fluorine has 7 and it just wants 1 more. So 1 fluorine will take 1 of my valence electrons. So I would need a second fluorine. That's why I write CaF2. I would need 2 fluorine atoms to satisfy my 2 electrons that I'm trying to lose. All right, the name is the name of the metal, calcium, and then F is fluorine, so I put fluoride. When you name it, you want to end it in "ide." Let's take the next one. Zinc is Zn with a +2. Chlorine is Cl with a -1. I crisscross those charges and get ZnCl 2. And I write it out, zinc. And because zinc actually is in the middle, I could put the 2 on there for a transition metal, chloride. Zinc only has one oxidation state. It's only ever a +2. All right, I will do one more with you. Sodium is Na, and that's a +1. Oxygen is -2. I crisscross and get Na2O. And the name would be sodium oxide. All right, you can go ahead and do the barium and nitrogen one. I'm going to scroll down a little bit. Here I give you formulas. So the formulas tell you what it is. First of all, I can name it. This is magnesium, Br bromide. If I reverse the charges, the 2 came from up here and the 1 over here, so it was Mg + 2, and it was Br - 1. And I always want to look that up and make sure it was correct and that it wasn't simplified. So when I look up Br really is a -1, and Mg really is a +2. So this formula is not the result of simplifying, that's correct. So, and the 2 elements are magnesium and bromine. I don't have a lot of space, but that's why I'd write it in there. So you go and do that for these 2. And then I'll move down to some of these names. I'll go here to this last one. Calcium iodide. So I look up calcium, Ca is a +2. I look up iodine, and it's a -1. I crisscross my charges, and I get CaI2. That would be my formula. And it obviously formed from combining calcium and iodine. All right, moving right along, transition metals. So if you look from groups 3 to group 12, those are my transition metals. And they have multiple oxidation states, meaning that titanium, it could lose 2 electrons, or it could lose 3, or it could lose 4. Over here, vanadium, it could lose 2, 3, 4, or 5. This one, 2, 3, or 6, 2, 3, 4, or 7, 2, or 3. The reason why, they have some inner shells that aren't quite full, so they actually have options and have been found to lose a different number of electrons depending on who they're bonding with in nature. When you want to figure out their name or figure out their formula, you can simply do reversing of the crisscross. So this is what you do. The 3 came from this titanium, the 2 came from the oxygen. Always check the nonmetal and make sure that really is its charge. So I go to oxygen, it really is a -2. So that tells me this was not reduced, it's perfect just the way it is. So to write the name, I would write titanium 3 oxide. Now, middle metals need middle names. So if it's anywhere in 3 through 12, its middle name is its oxidation state in a Roman numeral in parentheses. So that's how I got the name titanium 3 oxide. Titanium had a +3 charge. Now we'll go over to this one. If I crisscross reverse, I would get a +2 and a -3. I look up N and make sure it really is a -3. It is, so that's perfect. So I write nickel 2 nitride. So nickel 2 nitride. 2 because that's the charge that nickel had. Nitride, I always want to end these in an IDE. All right, FeO. There's no numbers there, so I just look up the non-metal. It does me no good to look up the metal because middle metals have multiple numbers to choose from. I want to go with the non-metal because there's not choices. So O is a -2. If O is a -2, that means it has gained 2 electrons. It got the 2 from iron, so iron must have been a +2. They had to have balanced each other out, and when they were simplified, they got reduced to 1 and 1. So the name of this would be iron 2 oxide. Over here, copper and chlorine, I can look up Cl, or I can just reverse the charges and do +2, -1. Oh, somebody asked me, how do I know this is always a plus and this is always a minus? That's because the first one is always the metal. The metal is the left side loser, so it's always positive. The second one's the non-metal. It's always negative because it's gaining electrons. I look up chlorine and make sure it's a -1. It is. So that tells me copper really does have a +2 charge. So I write copper 2 chloride. Again, if you feel like I'm going really fast or you want to go over it, just stop, rewind, play it again, and make sure you star where you would like to ask me questions the next day. All right, here I've given you some names and I want you to write the formula. So titanium 3 means that the Ti has a +3 charge. Chloride, Cl, I look it up, it's a -1. Now I crisscross and I get TiCl3. That would be the formula. Vanadium 4, so a V with a +4. Sulfide, sulfur, I look it up, it's a -2. So I get V2S4, and if I can reduce it, I should. So this I can reduce to VS2. The last two, manganese 3 oxide and gold 1 bromide, I want you to do for practice. All right, Lewis dot diagrams. I call this as easy as A, B, C, D. So A stands for atoms. Make sure you include all the atoms and separate the positives and negatives. You shouldn't line them up next to each other. A negative wouldn't like to be next to another negative. So spread them out. B for brackets, C for charges, D for dots. So I'll go ahead and do a couple with you. Fe and O. I know O is a -2, so Fe must be a +2. I have two atoms, Fe and O. A for atoms. B for brackets. I put brackets on both. C for charges. This is a +2, this is a -2. This is also a place where you can stop and check your work. These atoms should add up to 0 charges. So one atom with a +2 and one atom with a -2 gives me a total of 0. That means I did it right. I did my crisscrossing right. I have the right charges. Now, iron has lost its 2 electrons, so I do not put any dots on here. Oxygen used to have 6 dots, 6 valence electrons. It now has gained 2. So that was 6. It gained 2 from iron, so now it has 8. If I go down here to the gold one so that I do another one that has a name, gold 3 iodide. Gold is Au, and that's a +3, because it tells me right there in the name that it's a +3. Iodide, I look it up and it's a -1. So I crisscross and I get AuI3. To draw the dot diagram, I want to put Au in the middle, and iodine here, and iodine here, and iodine here. So I separate them up, but they're all going to be negative, and I don't want them to be too close to each other. So A for atoms. B for bracket. C for charges. -1, -1, -1, +3. You'll notice it does come out to 0. A +3 -1, -1, -1 gives me 0. Now iodine, they all had 7 dots. So I'll go around and put the 7 dots. They now have 8 dots because Au had 3 dots. It gave 1 dot here, gave 1 dot there, and gave 1 dot there. So that's why you needed 3 iodine to satisfy that gold. So again, I want you to go through, do the dot diagrams for the rest of these. If there are things that you're having questions about, please star them so you can ask me first thing in class. All right, our last slide here today are properties. So what ways do ionic compounds behave? And I wrote over here, think salt. Salt is a perfect example. NaCl is a metal transferring electrons to a nonmetal, so it behaves in a very specific way, and you can picture salt. Salt is hard, crystals, and when I say hard, I automatically am assuming it is a solid. The crystalline structure is because there's so much attraction between these molecules. To melt salt, you would need a very high temperature. So that is a property of ionic compounds. They melt at a very high temperature. They boil at an even higher temperature. So melting is to go from a solid to a liquid. Boiling is to go from a liquid to a gas. It's got to be thousands of degrees. Next property, strong attractions. And you can think of it like this. NaCl will keep lining itself up like this. Na is positive, Cl is minus. This Na is positive, this Cl is minus. This is positive, this is minus. Well, these are attracted to each other, and these are attracted to each other. So that's how it actually forms a crystal. It dissolves in water. If I had salt in my hand and I had a cup of water, I could pour it in and it would dissolve. And then lastly, to conduct electricity, it will not conduct electricity if you just hold salt in your hand and you use one of those conductivity testers. It won't light up, it won't conduct. But as soon as you put it in water, the ions can now move about, and you need moving ions to conduct electricity. So when you put salt in water, because it will dissolve and it will form ions, it will conduct electricity when it's aqueous. All right, I hope that all makes sense to you.